We've come to lecture number 19, which is entitled The Equivalent Circuit Parameters and the Measurements of the Equivalent Circuit Parameters for use in calculating torque and plotting torque speed curves. And this is all relative to the induction machine. The classical and oldest method for calculating the performance of AC induction machines has been the use of a single-phase equivalent circuit coupled to the circuit of the squirrel cage rotor. And this method of calculation has been very popular for the last 100 years, and it's used for basically three purposes. One, first reason is for teaching and understanding the principles of induction machines. And second, electrical engineering teams that are involved with the design of an inverter, and they must commission their inverter with the machine it's supposed to drive for the first time. They need to use equivalent circuit parameters to put in their models that they use with MATLAB and Simulink and other tools like that, so that they can get their motor and drive system operating correctly for the commissioning process. And the third reason is that this tool was actually used to predict the design of motors before we had computers. Before we had simulation tools that use computers to simulate the performance of machines and finite element solvers and things like that. Why the equivalent circuit was used to predict the performance curves resulting from their design process. All the equivalent circuit parameters were actually calculated using classical formulas, and then that's how the design was predicted. But eventually, after the motor was built, then validation was performed by measuring all these these equivalent circuit parameters and comparing it with the simulated results. And this is the equivalent circuit, and the circuit on the left side represents, as we all know, the equivalent circuit of a single phase of a three-phase induction machine. And these are all of the characteristics here. There's the terminal voltage across the terminals is for the stator. That's this, and then the stator, the total stator current, the resistance of the phase of the stator phase, and the stator leakage reactance is this term. The rotor leakage reactance, the rotor current, and the rotor resistance, and then the magnetizing reactance, and finally the magnetizing current. So the magnetizing current is magnetizing the circuit, and the rotor current vector is producing the torque in the machine. So these values can all be measured with an actual motor, but they can also be calculated. And the supply current that we saw in the previous slide, the phase current or supplies current, that's broken up into these two current vectors, and that equals the magnetizing current squared and the torque producing current squared. The root of those is the supply current. So the working current or torque producing current circulates in the rotor cage, and the flux vector drives the regulation of the two current components of the phase current, as we'll see in a diagram later. Using constant volts to hertz ratios, variable speed control is used, and that controls the magnetizing current by keeping the ratio of the voltage and the frequency the same. This works pretty well for open loop systems and gives decent torque speed performance, except at very low speeds. This only works down to about 5 hertz. The standard test for measuring the equivalent circuit parameters, there's 3 tests. The DC test, which is a line-to-line resistance, which is a very simple thing to make, and then the load the no-load test and the locked rotor test. And using those two tests, you can measure all the other parameters. The stator phase resistance is measured by applying a DC voltage across the stator windings, measures the DC voltage and current, and then calculating the resistance from that. You can use a very accurate resistance bridge to measure that as well, of course. The no-load test is conducted by taking the motor and uncoupling it to any load. It's a coupled shaft. It's a free shaft, and apply 3 balanced AC voltages to the terminals at rated frequency, and measure the current and the voltage and determine the input power. Record the total losses, the windage, the ohmic windage, and core losses and friction. The blocked rotor test, this is a test where you lock the shaft somehow so that it can't rotate and it can't move, and you apply 3 balanced AC voltages at about 1/4 hertz, very low frequency, and adjust with the shaft locked and it's trying to rotate, of course, it's drawing current, and adjust the AC voltage using a variac. You can use a 3-phase variac to produce the rated current, and then measure the voltage and measure that current, and then from that you calculate the input power. So that's how the equivalent circuit parameters are measured, and there's lots of textbooks and other procedures to make those that most inverter guys are familiar with. Let's just look at the torque speed curve for a moment and see what happens when you adjust the voltage. What happens to the torque speed curve? This black curve is the fundamental torque versus speed curve with some fixed voltage and frequency. So we're going to look at changes in frequency and voltage relative to that one. So if we decrease the frequency, then all these curves which are kind of congruent. They're the same shape and proportion, but the speed at which they start just decreases. If you increase the frequency, you'd have a family of congruent curves or similar curves that would have higher synchronous speed, but the slip would be about the same, and of course the operating points would occur at a different place. If this is a fan load plotted on this, and you increase the frequency, certainly the fan is going to go faster, but the faster you go, the higher the torque because of the shape of the load torque. Now, if you change the voltage, if you decrease the voltage, then that changes the slope. As you see, these blue curves here are the breakdown torque is reduced if you reduce the voltage in both cases, and also the slip changes. So there again, with the same load, with the decreased voltage, you'd be operating at these points here, or no, these 2 points here, But with an inverter control, you can control both of these. So as we'll see, we're going to define an envelope that a machine and an inverter together will run with. And I've shown this plot before. This is the same thing in the motoring area and the generating mode, where some prime mover spins the rotor faster than synchronous speed up to a maximum amount, and so you get generated power at the leads. Now here's a full 4-quadrant plot of a bunch of different torque speed curves. This is a whole family of torque speed curves that have been plotted. These could be measured, except there'd be a thermal problem to measure them. So this is probably this data, I believe, was taken by calculating the torque speed, this family of torque speed curves, and then plotting them all on one graph so you can study and understand the envelope of what the capability of the machine is. So if we draw a curve fitting line that covers the outside extremity of this motor, and this inverter driving this will operate at any load point inside that envelope in any of the 4 quadrants. So that shows you what the capability of a motor is with an inverter driving compared to what its capability is from a curve like this, operating off the grid at fixed voltage and frequency. But by putting inverter on it, you can operate over this huge speed range and have very high starting torques just by controlling the magnetizing flux as a function of frequency, and that's done by controlling voltage. And there's no signs of saturation here. We're still able to achieve these peak torques at low speed. So basically, a motor like this with this kind of control, with flux vector control, can produce torque right down to 0 speed. The reactance components are the most difficult things to calculate, and there's been many famous motor engineers down through the years that have come up with their own methods to what sort of factors and calibration or fudge factors they use for different kinds of machines and different shaped bars that helps them to calculate the leakage reactance. Let's see, I believe this says, they're both stated, this should say rotor leakage reactance here. That's a mistake, so cross that out and let's call that rotor leakage reactance. And that's made up of several terms. The total reactance is made up of several terms: slot leakage, end ring leakage, belt linkage, zigzag leakage, and skew leakage. In stators, there's very seldom any skew, but there can be. The reactances and resistance of the machine has an effect on power factor and efficiencies. If the power factor, well, we always want a high power factor, that's for sure, but a low power factor means that it takes too much magnetizing current. And what would cause that would be too high of leakage. And the more poles you have, the greater the leakage. So that's one of the reasons why high pole number machines are hard to get high power factors. So the breakdown torque and starting current are determined by leakage reactance, and excessive starting currents causes saturations near stall or between breakdown and stall. And so this starting current has to be controlled by the ratio of the voltage and the frequency. And of course, the stator and rotor ohmic losses are determined by the resistance measurements. Starting torque is inversely proportional to the rotor resistance. We saw that before, where the voltage has to be boosted. And torque versus speed is affected by the rotor resistance. So for inverter duty motors, we want to have a very low resistance, and we'll take care of the starting torque. This statement of starting torque inversely proportional to rotor resistance, that's true of a machine that has to start at a fixed voltage and frequency that's not proper for starting. So that's why the inverter, the flux vector drive, mitigates this statement that starting torque is inversely proportional to the rotor resistance, because when it's driven by inverter, it isn't. These are the formulas to calculate the torque speed curve for the equivalent circuit. So these formulas can be put in a spreadsheet, and you can generate the curves for a bunch of different values of voltage and frequency, and then curve fit those and make a plot. As we said before, the use of the torque speed curves are very important. It defines the breakdown torque and the starting torques, of course, at fixed frequencies. So to determine what a motor and a drive together is capable of, you run enough of a family of the curves to define the envelope, like we saw in this view here. But there are many applications now require an operating envelope. Here's a requirement for a torque speed performance curve of motor that has to have a constant torque range for a vehicle traction, for example, and then a constant power range. So how do you how do you define the capabilities of the motor you've designed to fit in that envelope? Certainly that black plot has to fit inside this envelope. And a simpler way to do that would be to optimize the voltage and frequency for, say, 5 or 6 load points. This is the max speed that you need to produce torque at, and a couple of points in the constant power range to define the shape of this curvature, and then a point where the peak of the constant torque point is. You need to identify that one, and that's really the same as this one. But if you optimize the magnetizing current and the torque producing current for these 5 points, you've identified this envelope, and you've shown that the drive you have and the motor you have designed, those together will give you this operating envelope. And that's the importance of the torque speed curve. And in the application then, when this is applied, this motor will operate anywhere within that envelope. Now the only other thing that is done is this is a rated current here. Let's define it as a rated current thermally, so that this is a high current, this is where the peak torque, and so we might define that as rated torque and rated continuous power. But you could also use the same analysis and determine a peak constant torque and constant power range that maybe could operate for 10 seconds or 20 seconds or a minute or 2 minutes, used for accelerating the car or going up a grade. And that's a requirement too, so you can use the same process to identify that envelope. And here's the two vectors that you want to determine to provide the right magnetizing current and the torque producing current, and get those out of the phase current that comes from the supply or the inverter. And the power factor is it's really the angle in here. The cosine of the angle here is really the power factor. You want this you want the magnetizing current to be as low as possible for high power factor. And if you have high leakage, then it requires more magnetizing current, because you're leaking too much of the flux from that's created from the current. So I guess that's the end of the lesson. Thank you very much.